EEG signal processing. So we will see two parts. So one is analysis and second part is classification. So if you see in real life, the most of the signals that we see, they are non-stationary, non-linear and noisy. So there's 3N rule. And in this talk, we will see non-stationary signal processing methods, which can be considered as advanced signal processing techniques. And also, if you see literature, most of the researchers, they apply machine learning directly to classify these biomedical signals. And one such example in this talk we will see, that is electroencephalogram EEG signals. And when they perform this machine learning for classification of that, then there is a lot of demand to come up with the diagnostic features which can give you nice interpretation of the disease. So there is actually a lot of interest in the literature to combine this advanced signal processing with the machine learning. And so that we have nice set of features, nice analysis, interpretation can be done. So that kind of work is coming with the new direction, which we call interpretable AI, explainable machine learning, explainable artificial intelligence, etc. So in this talk, we will see the use of signal processing and machine learning techniques to design automated systems, expert systems, intelligent systems, which can identify this normal brain signals and abnormal brain signals. And there is actually a lot of use of such kind of systems, and that is in general way in literature we call that computer-aided medical diagnosis. Even like if you implement these algorithms in the computer, that computer itself can be used to perform diagnosis. Some hardware also can be designed. Suppose somebody is working in the field, then that wearable device in this, by using such concepts, can be actually developed, and that can be carried by the patients or people to perform diagnosis or detect the disease in initial stage. So if you see rural areas and villages especially, like there is sometimes there is no doctor and sometimes there is very less doctors. So such kind of systems, whatever we have proposed in software, that can be integrated with smartphone, mobile, computers, and they can be used in rural areas to detect the disease at the initial stage. And once you detect the disease initial stage, so timely treatment can be carried out. These patients actually can go to urban areas, and where a diagnosis can be done timely, and timely treatment can be performed. In urban areas also, if you see, the patients are actually more, number of patients are more, and doctors are less, neurologists are less. So such kind of systems which can help doctors, neurologists to assist them to perform efficient diagnosis. So there is a lot of applications of such kind of work in rural areas as well as urban areas. And in this talk, we have considered three application domains. One is epilepsy, second one is sleep stages, classification problem, and third one is emotion detection. So these all three are very important. And if you see, epilepsy is a neurological disorder, and you might have seen in rural areas, so there's people struggle a lot when they get epileptic seizures. It is very serious disorder, and if you detect it timely, then you can bypass this attack. There are epilepsy drugs are there, so that is a lot of applications. It is useful concept. And the sleep stages, that is also very they are highly correlated. Even you are sleeping, you don't know you have various sleep stages, and then detection of sleep stage is very important part of the sleep diagnosis. And emotions, these days, you see human machine interaction, there's new area is coming, and emotions are very important. If you understand emotions of a person, then you can it is helpful in many ways. You can accordingly you can behave with that person. It is very useful in the family also. Like if you know emotions of the family member, then nice behavior can be done accordingly. And also newborn babies, they are not able to speak you, they are not able to communicate. Based on the emotion detection using such biosignals, we can understand what kind of emotions they have, and accordingly we can interact with them, and we can understand them whether this treatment is showing effect or not. So with this background, let us start this talk. So I will share my slides. Are you able to share slides? Yeah, Professor Hemant, slides are visible. Am I audible? Oh, oh, okay. Thank you. Thank you. So today's talk is on advanced signal processing for EEG signal analysis and classification. So this is the overview of this talk. First, we will see introduction, then empirical mode decomposition based features for analysis of normal and seizure EEG signals will be explained. Classification of seizure and non-seizure EEG signals will be presented, and then we will see detection of epileptic seizures. And after that, we'll see time frequency image based features for classification of sleep stages. And after that, multivariate decomposition based features for human emotional classification will be explained. And in the end, conclusion will be provided. So in this talk, actually, this EMD method is there, but we will also see the way the need of EMD method. So basics of signal analysis technique, basic signal analysis techniques also will be explained. And this talk actually will give you the some set of problems where you can apply deep learning algorithm, advanced machine learning algorithms, convolutional neural network, advanced signal processing. So here in this talk, this is a basic talk. You will get actually exact problems where you can work from implementation point of view, from signal processing point of view, from machine learning point of view. So various ways from hardware implementation point of view. So human brain is very complicated and it is highly nonlinear system. And if you see like whatever you are thinking, that actually that is not same. So it changes different time. And even if you record this electroencephalogram EEG signal, which is the actually very useful signal to measure the electrical activity of the brain. And it actually, if you record 10 times, then every time is different. So it is so much variable. So this electroencephalogram, which we call EEG signals, they measure the electrical activity which is generated by the neurons in the brain. And this EEG signal is a very useful clinical tool in order to investigate different physiological and pathological states of the human brain. If you have any disorder, brain-related disorder, neurological disorder, and if you go to hospital, then actually the doctors they first they record your EEG signal, and based on that they read it. That reading of EEG signal, understanding EEG signal, that actually method generally people use, that is manual, and it has many problems that we will see in this talk. So there is a lot of interest to develop automated systems to understand that EEG signal and to read that EEG signal to understand the disease. So the quantitative analysis of EEG signal is a challenging task because this EEG signals, they have complex and irregular nature, and also they are non-steady signals. So non-steady signal means like we use mathematical models to represent the signal, If any of the parameter is changing with respect to time, then we call them a non-stationary signal. So this EEG signal, if you use mathematical model, even if you use a small length of the signal and to represent it mathematically, then actually it has been found that then parameters are also varying with time. So that is actually non-stationary. So it is whatever signal actually you consider, even a small length, even 30, 35 samples, that is also actually non-stationary. So due to that reason, it is very difficult to actually perform quantitative analysis of these signals. And generally, what actually we do in hospitals when we go for diagnosis or treatment of the brain diseases, then doctors actually they record your signal, they print it on the paper, and then they perform visual scanning of that printed waveform. So such kind of method, it is very time consuming and it may be inaccurate, it is very complicated and is subject to judgment and suffers from human error. So you might have seen, let us have opinion of other neurologists. So that actually sometimes they two persons can have different opinions on a same EEG signal. So they subjective in nature and it is performed by trained professionals. So a lot of expertise is required, a lot of training is required. So that cannot be used by the common people. And disease doesn't see whether you are common or whether you are expert. It can be with anyone. So in rural areas, suppose if you want to use such kind of method, then actually difficult to do. So that this actually, if you come up with such features which can be understood by the common people, that is very good for the diagnosis of the brain disease. So we have proposed such features, such methods, which even illiterate people also can use. For disease, actually, everybody is same for this. Disease doesn't see whether you are illiterate, literate, or any kind of profession, disease can come to you. So due to these all reasons, there has been a lot of interest in the literature to perform actually three kind of tasks for these intelligent systems for brain diagnosis, brain disease diagnosis. That is, first one is the analysis part, where people develop signal processing methods, signal analysis techniques. And second one is feature extraction. So we actually develop features, their well-behaved diagnostic features. And third one is classification part, where we use various machine learning methods. So when combine these three approaches, three concepts, then actually we have this intelligent systems, and nicely they can actually classify these EEG signals, whether it is normal or abnormal. So the first part of this talk is analysis, classification, detection of epileptic seizures. So we have developed actually three approaches for analysis, detection, and classification for the seizures. And these all seizures are not epileptic seizures, but any seizure, if it has repetition, particular frequency, then we call it epileptic seizure. So epileptic seizures, they are the result of the transient and unexpected electrical disturbance of the brain. So in the brain, there are neurons. When these neurons they synchronize to each other, generate very high electrical activity, which results actually epileptic seizures. So that once all neurons they synchronize together, they generate high electricity that actually disturbs the brain. Brain is the master of the body, and brain is disturbed, and everything is disturbed. So it is very serious disease, and it affects around 2% population of the world. And we have proposed area parameter for analysis of normal and epileptic EEG signal. Normal means that person never had epilepsy disease, and seizure epileptic seizure means that person has seizure disease, epilepsy disease. And second, the bandwidth parameters for classification of seizure and non-seizure EEG signal. Non-seizure means seizure free and normal. Seizure free means earlier they were having epilepsy disease. Now treatment has been done. Now they are disease free. They are seizure free. No seizures they have. And the third method, the instantaneous area for the automated detection of the epileptic seizures. So these all three methods will be explained in this talk. And this actually in 1998, this empirical mode decomposition method has been proposed in the literature, which is data dependent, and you don't need to design basis functions from your side. So that was a new direction of the signal analysis, signal processing since 1998. Before that, if you see the Fourier transform, short time Fourier transform, wavelet transform, in all these methods, we design basis functions from our side. And we represent these signals, for example, EG signals in terms of such known functions, which we know. So in that way, this unknown signal, for example, like EEG signal, we represent in terms of known signals. But these known signals, which we call them basis functions, basic signals, building blocks, and they are actually designed by us. So we are representing this unknown signal in terms of known signals. So this unknown problem actually becomes simpler. So easy to understand in terms of known functions. So that's why the actually idea in this Fourier transform, short time Fourier transform, wavelet transform based analysis techniques. This empirical mode decomposition, 1998, that actually Edward Wang and others, they have developed this method. This has come from computer science. So they don't use any analysis synthesis equations like Fourier transform, mathematical way of formulating them. On the other hand, it is actually based on an algorithm. So there is an algorithm, and you apply this algorithm on the signal, and then actually this algorithm will give you the decomposed components, and then similar kind of analogy that we have for Fourier transform, then we represent signal in terms of such decomposed component that we call intrinsic mode functions, IMFs. So that actually signal is represented as a sum of IMFs, and these IMFs, they are obtained by the simple algorithm, that is actually. So that is very simple algorithm that we'll see. And so these are the three frameworks that we have proposed. So it is actually expecting that when you use such kind of algorithm, such kind of decomposition method, which is data dependent, data adaptive, and that actually can give you meaningful components, which can have a physiological interpretation, and that actually that might not be in the case of Fourier transform, short time Fourier transform, wavelet transform, where basis functions were designed by us. So here, so due to that, this direction of the actually signal decomposition technique has become popular, and a lot of work actually people are applying, and they are developing a lot of signal analysis technique motivated by the EMD kind of approach. So, so in this first we have EEG signals, and then actually we decompose in terms of intrinsic mode functions using empirical mode decomposition method. Then we apply Hilbert transform to each IMF to get analytic signal representation. And then first method, we extract area feature based on the modified center tendency measure. And then we apply Kruskal-Walsh statistical test. And then actually it gives you statistically significant difference between normal and seizure EEG signals. And second methodology, this analytic IMFs, we compute amplitude modulation and frequency modulation bandwidths. And then we have given these bandwidth as an input to least square support vector machine classifier that actually classify automatically seizure and non-seizure EEG signals. In third methodology, we actually use a statistical area feature together with decision rules, and which actually gives you epileptic seizure detection. So these all three methods we will see in this talk in proper way. We will understand it how they are working. So for the study purpose, we have taken EEG dataset 1. So this EEG dataset, which is publicly available at the University of Bonn, Germany, and which is actually commonly used for the epilepsy cases. So like there are two commonly used databases. One is this Bonn database, and second one is Academy-MNIT database. So that actually, so here this data set includes 5 subsets: Z, O, NF, and S. So subset Z includes the EEG signal recorded from eyes open condition, and subset O includes the EEG signal recorded from eyes closed condition. Subsets N and F, they are recorded from the seizure-free subject, from the seizure, and S includes the signals from seizure subjects. So in that way, actually, this each class or each subset contains 100 EEG signals, and duration of these signals is 23.6 seconds. And sampling rate of EEG signals in this database is 173.61 Hertz. And these EEG signals have been recorded with the same 128 channel amplifier system using common reference. So like they have been recorded by the neurologist, and they have actually detected manually by visual inspection which EEG signal is seizure, which is seizure free, which is, so according to that actually that is segmented, and these signals has been arranged in the form of subset so that they can be used for the research purpose. So now we will come to empirical mode decomposition method. So this EMD method actually is suitable for nonlinear non-static signal analysis, and is an adaptive method and does not require condition of stationarity of the data. Like in case of Fourier transform, we assume that signals are stationary. In short time Fourier transform, we assume that within window our signal under analysis is stationary. That assumption is not required here. And data dependent method does not require design of basis functions like wavelet transform. Like in post or Fourier transform, we design sinusoidal functions. In case of short time Fourier transform, we design windowed sinusoidal functions. In case of wavelet transform, we design mother wavelet. So this all kind of designs are not required here. And the EMD method decomposes a signal into set of narrowband interaction mode for IMFs. And these IMFs can be modeled using amplitude and frequency modulated sinusoids. So the sinusoidal functions, their parameter, they change with time. Then actually that model is AMFM model. So here, in case of Fourier transform, signal can be represented in terms of sinusoidal functions. Similarly, in EMD, we can say this is more general form of the Fourier transform, where signal can be represented as a linear combination of the time varying sinusoids. So this amplitude and frequency modulated sinusoids. So now the sinusoids parameters will vary with time. So that is a more general model, and you can say that we are representing signal in terms of non-stationary basis functions. On the other hand, in Fourier transform, whatever model we are using, that actually requires stationary basis functions. So each IMF which we obtain from this model, that actually that satisfy two basic conditions. So first condition is the number of extrema and the number of zero crossings must be the same or differ at most by 1. So this condition ensure that whatever IMF you obtain, they are like sine cosine function. And the second condition, the mean value of the envelope defined by the local maxima and local minima is 0. So this condition ensure that whatever actually IMF you obtain, that is symmetric in nature. So by satisfying these two conditions, we ensure that whatever IMFs actually we have obtained, they are symmetric in nature, they are like sine cosine functions. And based on this residual concept, actually these first, like you have designed by satisfying these conditions, you obtain first IMF. Then first IMF will be subtracted from the signal, and then we get residual, and then we repeat the same process for whatever we have done for first IMF to get the second IMF. Now next step, first IMF, second IMF, both will be subtracted from the signal, and then we will repeat the same process on this residual. So in that way, you get a third IMF. So in that way, you get all possible IMFs. In the end, only residual will be left, from which further IMFs cannot be derived. That is either monotonic function or from which it doesn't have oscillatory nature. So in the end of the decomposition, signal can be written as a sum of these IMFs. For example, capital M IMFs. So then this is equation 1. You can write signal in terms of linear combination of M IMFs plus last one is residual, from which further IMFs cannot be derived. So that is actually this is the model. After algorithmic process, we assume that this signal has actually can be represented by the all IMFs, a sum of IMFs. So this is one example of empirical mode decomposition of EEG signal. So you have first signal that actually this is a signal, and this here you can see this is epileptic seizure EEG signal. So here it has spikes, and it has large amplitude. So that actually these are the two important features when you go to hospital and doctors see for epileptic seizure detection. So when you decompose this using empirical mode decomposition method, then actually you have first IMF, second IMF, and this last residue. So first IMF is actually like a highest frequency present in the signal, and that's the lowest scale of the data. So that it gives you the detail. And eighth IMF, that is actually lowest frequency of the data and largest scale, that is the approximation. So that actually in that way, this Patrick Flandrin and his team have shown that whatever actually these IMFs you obtain, they are actually similar to wavelet transform. So like here you don't need to design wavelet functions, you don't need to choose number of labels. Without doing that, it can give you the number of components like approximation detail, different degree scales components. So that is actually beauty of this method. So that is adaptive. You don't need to design. You don't need to know which mother wavelet should be used. There is no thumb rule which will suggest what wavelet should be used. And also, you don't need to know number of labels. Automatically, it will give you number of labels. So that is now actually this new direction has come. So actually, when you see this Fourier transform, we are representing signal in terms of sinusoidal functions. And these sinusoidal functions, they have infinite spread in time domain. They are periodic in nature. So due to that, actually, resolution is proportional to 1 upon spread. Since spread is infinite in time domain, so the sinusoidal functions, they have zero resolution in time domain. So due to that, actually, or zero localized in time domain, they are not able to represent the signal which are non-stretching in nature. They are changing with time because this Fourier transform, sinusoidal functions, they are not changing with time. So due to that, this Fourier transform is not suitable for non-stretching signal representation. Then this short time Fourier transform was proposed in the literature, and where what we do, we divide the signal into different segments. In each segment, we assume that signal is stationary, and then we apply Fourier transform. An arrangement of these Fourier transform gives us short time Fourier transform (STFT), and this method it requires actually size of the window and type of the window. There is no thumb rule which will suggest us what should be the size of the window, type of the window. So for example, you have low frequency component, then analysis window should be wide enough. If you have high frequency component, analysis window should be narrow enough. So that flexibility is not there in the short time Fourier transform. So motivated by that, this wavelet transform was proposed in the literature where we use scale concept. So when scale, like you see signal at different scales. So that actually is a very important concept for biomedical signal processing. Like for example, if you see legs of the elephant looks like a tree. But if you see elephant, tail of the elephant looks like a snake. But elephant is not a tree, elephant is not a snake. If you want to see elephant like an elephant, then you have to see a proper scale. So that actually, how to select that scale, that is missing. Nobody knows. So that what we do in the wavelet transform, we do analysis with all possible scales. And we believe that at least one scale will match with the required scale. So in that way, we find the best one. So that is actually, that is known as multi-resolution analysis. So we are doing analysis with all possible scales and we find which one is matching with that. But in wavelet transform also, good thing is that it can be implemented by this filter bank that we call discrete wavelet transform. We have signal, we apply low pass filter, high pass filter, then downsample by 2 each part, and then we approximation detail. But that method also, we should know how many number of labels are required for the decomposition and which mother wavelet is required. So there are many mother wavelets and we don't know which mother wavelet is good for analysis. There is no thumb rule. So motivated by that, this empirical mode decomposition was proposed. And the good thing is that actually here you don't need to design basis functions, don't need to design mother wavelet, you don't need to know skills, whatever required for the decomposition. Despite that, here you can get the similar kind of decomposed component. When you see the spectral properties of these IMFs, they look like the wavelet component. So this is actually, so this has been come as an alternate of the wavelet transform, but same time it doesn't require design of the wavelet, and number of levels don't need to know a priori. That is actually a good thing. So after once you have this analytic signal represent this IMFs, then actually this analytic signal representation has been computed for these IMFs. So the proposed method is based on analytic signal representation, which we compute using Hilbert transform. So analytic signal, ZT of signal CT can be defined as ZT equals CT plus J C cap T. So that is AT e to power J5. So this is like complex signal. So it is amplitude, time varying phase. So that is actually complex representation. And this analytic signal representation of mth IMF is given by the equation 2. And here, and that actually, this good thing is that this analytic signal representation for this particular IMF, we obtain that actually satisfy two conditions. First, plot a direction of rotation, and the rotation in the plot at unit center. So these two properties they are very important, and that actually help us to define the feature, very good feature which can be used for the epilepsy diagnosis. So here you can see, if you see analytic signal representation of EEG signal without any decomposition, then it has multiple centers, and it actually is not having any geometry, any specific geometry. So it is difficult to find out any area for that, any compute area. On the other hand, if you see this IMF 1, 2, 3, 4, they are circular in structure, circular in nature, and circular pattern. They have circular pattern, and it is easy to compute area because they have unit center 0, 0, and they have a direction of rotation also there. So that actually help us to define area parameter as a indicator of the epilepsy. And good thing is that actually we have also proposed how to compute that area. So that mathematically. So the proposed area feature and modified center tendency measure. So if n is the total number of points and r is the radius of the central area, then modified CTM is given by the equation 3. So here CTM, so this n is total number of points, and delta dn, that is actually coming out 1 if this point is less than radius r. So otherwise it is 0. So CTM will tell how many points actually are lying for a given radius. So like we in this work, 95% CTM has been used to compute the area of analytic IMF, and the area A is computed by using the following equation: A equals to pi r square, and r is here r CTM for 90%, 95% CTM. That radius has been selected to compute the area. So once you have this like area, then we have proposed instantaneous area of analytic IMFs. So the instantaneous area is measured from the trace of the windowed analytic IMFs, and the instantaneous area at any point is computed by using a moving window method. So like short time Fourier transform. So we divide this actually IMFs into different segments, and each segment we compute the area, and then we interpolate it. So we get time varying area or instantaneous area. The chosen size of each moving window is L equals to 3840 samples, and this window size is uniform for all EEG signals. So based on the literature we have used that window size, and the sentence area of mth IM is defined by the equation 4, and then actually there is bandwidth. Generally, when we talk about the bandwidth, then actually it is spread in the frequency domain, and it's based on the Fourier transform. But there was a different kind of actually bandwidth which were defined by the Cohen and Lee in 1990. It was based on the non-stationary signal processing interpretation. So like for any signal, if you see the bandwidth, it depends on the two parts. One is amplitude modulation, second one is frequency modulation. So there are two kinds of bandwidth. First one is this equation 5, you can see bandwidth AM, and second one is bandwidth due to frequency modulation, bandwidth due to FM. So now in real life, our signals, they are actually multi-component AM/FM signal. So it is very difficult to apply this formula. So first time actually in the literature, we understood that actually the use of empirical mode decomposition that can convert this multi-component signal, multi-AMFM, for example, EG, into mono-component AMFM signal. And then you can apply this formula for each IMF. So this formula can tell you each IMF how much bandwidth due to AM and how much bandwidth due to FM. And these measures actually have been used as a set of features to perform the classification between seizure and non-seizure EEG signals. So that is actually in this work we will see. So now we will see some results, analysis of normal and seizure EEG signals. So subset Z from the normal class and subset S from the seizure class. And this method can detect patients with epilepsy using EEG signals from normal people. And the EMD based decomposition makes possible to cover more than 95% of the data points which lie within the circle due to having circular form of analytic IMFs. So that is actually a good point. And the area parameters have been estimated for both the classes, normal and seizure, using analytic signal representation of IMFs of various window lengths. For example, n equal to 500, 1000, 2000, 4000 samples. And generally in medical applications, actually, we want to have analysis, window analysis or signal analysis at less number of samples, very less, as less as possible window size. Because it has two major advantages. So one is it reduces computational complexity of the method, which makes it suitable for real-time implementation. And second advantage is that actually is patient, it is comfortable because we have to record less data. So for patient also it is fine. So here you can see this from this figure, CTM in terms of percentage is plotted versus radius. So here you can see if you window size up to 4K, normal case, this around 300 window size, 300, that is actually covering CTM up to 100%. And normal case, like seizure case, a requirement of window size radius that becomes, there is actually nearly 1200 to get the 100% CTM. So this means like this case radius requirement for seizure case is higher. That is actually, it has more variability. And that in case of seizure, the requirement of radius is less in order to have 100% CTM. So that actually motivated us to come up with the method which can actually provide discrimination between normal and seizure signals using actually this kind of concept, this radius concept. So this, since radius is smaller and larger to discriminate these two classes, then actually we thought to use area parameter, and that is actually more interpretable. Anyone can interpret if area is becoming larger than it is seizure and area is becoming lesser than it is a normal case. So that nice interpretation of the disease can be done with the help of this actually parameter. So we have computed area, and now you will see the comparison of area parameters for normal and epileptic seizure intervals for windows length 4000 samples of different IMFs. So first IMF is P equals to 0, second IMF, third IMF, fourth IMF. All cases probability is 0. So probability, if it is less than 0.05, then we call this is Kruskal-Weiss statistical test. And if probability is less than 0.05, then we call it statistically significant difference. So these two seizure and normal classes, by using these 4 IMFs, they are actually discriminative in nature. That is actually done. And that is, so this means for 4000 sample size of the window, we have a statistically significant difference between these two classes. And here you can see this comparison of area parameter for normal and seizure EEG signals. Window length is 2048 samples of different IMFs. So first IMF, second IMF, third IMF, fourth IMF. In all cases, the probability value is coming out to be there's a statistically significant difference. And third case is comparison of area parameter for normal and epilepsy EEG signals. Window size is 2000 samples and different IMFs. First, second, third, fourth IMF. Probability value is 0. So that is actually statistically they are significant in all four IMFs. For window length, 1000 samples also we have obtained statistically significant results for this in terms of area parameter for this all four IMFs. For 500 samples also one can see these results often results are statistically significant, and for all IMFs in terms of area parameter. Now here same thing we can see in terms of quantitative values in terms of parameters that was in the form of box plots. Here you can see same thing in the form of parameters range. So subject normal and severe cases, and window size 500, 1000, 2000, 4000, and first IMF, second IMF, third IMF, fourth IMF, and you can see minimum, maximum, medium value. And that from this table it is clear that area parameter is actually higher for seizure case and it is lower for normal case. So that actually nicely can be used as an indicator for epilepsy diagnosis. And then actually in literature, if you see the many people, they have used machine learning also with the signal processing methods to perform the classification between normal and seizure EEG signals. And that you can see in this table. Nigam and others 2004, Srinivas others 2005, Kanatan others 2005, Polat others 2006, Subhasi 2007. And they use signal processing machine learning technique and they have got accuracy less than 90%, 900%. On the other hand, if you see our proposed method, we don't use any machine learning technique. Simple thresholding gives you 100% detection. So that is actually, so selection of the spoon depends on the type of food. And for example, if you want to have noodles, then we use fork. Because if food is discontinuous, spoon is discontinuous. So nicely, discontinuous food can be handled with the discontinuous spoon. So that is similar way, if you want to analyze EEG signal, then you have to use a very advanced signal processing technique that will match with the requirement. So actually here, luckily we have got such signal processing technique, empirical mode decomposition, which is perfectly suitable for the analysis, and so there is no need of classification. That is actually in this case. So even analysis itself is giving 100% detection. So that is it. Other cases we will see that there is a need of machine learning. So actually we should note at this point, sometimes analysis, if it is properly done, then you don't need machine learning. And sometimes analysis done by viewing features, you are not getting 100% discrimination, 100% identification or classification, then we go for machine learning. That actually is motivation. So one should not apply directly machine learning. One should see whether it is required or not. So now second problem is classification of seizure and non-seizure EEG signals. So the subsets Z, O, N and F, they are combined to form non-seizure class, and subset S form the seizure class. So this methodology can detect patients having epilepsy from the normal and seizure-free people. And EMD method can decompose nonlinear non-stationary EEG signal into set of narrowband AM/FM components or IMFs. So which facilitates computation of bandwidth due to amplitude modulation and bandwidth due to frequency modulation, which we call them BAM and BFM. And these bandwidth features help us to find the contribution due to amplitude modulation and frequency modulation components. So here you see bandwidth due to amplitude modulation of IMFs for seizure and non-seizure EEG signals. So first for IMFs, we are able to know the difference between seizure and non-seizure classes. And the remaining 5th to 8th IMFs, they are not able to show any difference. So these first four IMFs, bandwidth due to AM feature actually is useful. And similarly, we have seen in bandwidth due to frequency modulation of IMFs for seizure non-seizure signals. So the first four IMFs, this bandwidth due to FM, that feature is actually able to show the difference. The remaining case, 5th to 8th IMF, this feature is not able to show the difference. And then actually you can see both of them together. the bandwidth due to AM and bandwidth due to FM, and with all 8 IMFs. First 4 IMFs, the probability values are coming out to be nearly 0. So that is actually less than 0.05. So this is statistically significant difference by the both features. So due to that reason, we have used them as an input to machine learning classifier. Since these features are not able to give 100% separation like earlier case, so we found the need of the machine learning classifier. So machine learning will project actually these features in high dimensional space where nicely we can separate out them. So this remaining 5th to 8th IMF, the probability values you can see they are not statistically significant. So these bandwidth features for the first 4 IMFs are statistically significant small values of P. And this motivates us to use AM and FM bandwidth parameters of IMFs of each signal's input features in the LSSM classifier in order to obtain more accurate classification. So this least square support vector machine here we have used, and this is actually improved version of the support vector machine. So the effectiveness of the bandwidth parameters, bandwidth due to AM and bandwidth to FM in classifying the seizure and non-seizure EEG signals have been evaluated using a least square support vector machine classifier. So two class support vector machine, we consider the following decision function that you can see in equation 6, fx equal to sin wt gx plus v. So w is the L-dimensional weight vector, gx is the mapping function, v is the bias. So the sign actually gives you the two classes. If it is positive, then we say class 1, and if its value is negative, then we say class 2. So in that way, actually, this is binary classification problem can be studied. So this is a simple block diagram representation of LSSM classifier. So we have set of features. So we select training set, and then training set, we perform the training of this classifier, and then actually we select the kernel function parameters. And once you have this trained system, then actually we use remaining features as a testing set for this trained model. And then actually based on the output 1 or -1, we say that is whether it's seizure or non-seizure class. So in this work, following kernel functions are used. Polynomial kernel. So the mathematically polynomial kernel is expressed by equation 7, where there is the degree of polynomial, and the radial basis function, which is mathematically expressed by the equation 8, and here sigma controls the width of the RBF kernel, radial basis function kernel. And then Mexican head wavelet kernel function can be defined by the equation 9, and Morlet wavelet kernel function can be defined by equation 10. So that way this actually these kernels are designed. And in order to measure the performance of the classification model method that we have proposed, we have used 3 important parameters: one is sensitivity, specificity, and accuracy. Sensitivity, it is the proportion of the epileptic seizures correctly detected by the algorithm, and mathematical expression you can see here is TP upon TP plus FM. TP means true positive, FM means false negative. Specificity is the proportion of the segments without seizures correctly identified by the algorithm, and that actually Tn upon Tn plus Fp. Tn is true negative and Fp is false positive. Accuracy is the proportion of correctly detected seizures and non-seizures by the algorithm, and mathematical expression can be seen here: Tp plus Tn upon Tp plus Tn plus Fp plus Fn. So we can see sensory specificity and accuracy of IMFs with different kernels of LSPM classifier for classification between non-seizure and seizure EEG signals. So kernel functions, polynomial, RBF, Mexican head, and Morlet, and the parameters are L equals to 5, sigma equals to 0.4, A equals to 1, A equals to 0.6, and omega not equal to 0. So these are based on the trial and error concept. And these are the obtained parameters, sensory specific accuracy. And IMF 1, 2, 3, 4, we can see the minimum and maximum value of these actually performing measures. And from these actually table, it is clear that Morlet actually function, second IMF is giving best performance. That is actually so that second IMF is suitable for the classification between seizure and non-seizure signals. So this results also validated using a receiver operating characteristics curve, and where we have computed area under ROC curve. That is based on the polynomial RBF Mexican modeled kernel functions. And from this plot, you can see this modeled case area under ROC curve is coming out to be 1. So that actually it also validates that second IMF is actually is more suitable in order to have better classification performance for the seizure and non-seizure EEG signals. This is actually very important results. So this shows the feature space for testing set for the least responsible vector machine classifier modeled wavelet kernel function for second IMF of each signal. So here you can see this is shaded region shows the seizure case and non-shaded region that is non-seizure. So if you, for any signal in real life, if you want to check whether this person is seizure or not, then you just obtain it, record it, then decompose it using EMD method, select the second IMM and compute the AMM, FM bandwidth and project this feature space. So if it is coming in shaded region, then you call it a seizure, otherwise it is non-seizure. Very simple approach, and such kind of actually concept can be used in mobile, smartphones, computing devices, and that can be used for computer-aided medical diagnosis of the seizure, epilepsy. Many methods actually have been proposed in the literature for classical seizure and non-seizure signals. For example, Tajalas in 2000 and others in 2007, Okak in 2008, Liang in 2010, Liang others, Ling in 2011. And that is based on signal processing machine learning techniques. And our proposed method that is actually based on the empirical mode decomposition, bandwidth and least square support vector machine classifier, which gives you 99.5 to 100% classification accuracy. That is actually better than the other existing methods in the literature for this same problem. After that, we have actually proposed approach for epilepsy seizure detection algorithm. So till this point, any questions, please?
If you have the question, please type it in the chat box.
Yeah, then we will go for next part of this. So if you have any questions, please.
So someone has asked a question in medical image, and this is how can we use the EMD method?
In chat box?
Yes, sir.
In medical imaging, no?
Yes,
so
sir.
This empirical mode decomposition, whatever actually I have presented, it is for one-dimensional signal. Similarly, for this medical images, y-dimensional EMD, BEMD that we call, it has been proposed that can be used to obtain the two-dimensional intrinsic mode functions that we call y-dimensional IMA, BIMFs.
So sir, is the program function available, sir?
Yes,
for using
publicly
the
available for EMD also, BEM for bi-dimensional EMD also.
So is it, sir, publicly available or?
Yes, publicly available. So this actually they can search on Google, and many people they have developed algorithm, they have made publicly available.
Okay, okay. So another question is there from Neha. She's asking, what are the important features in the EEG signals?
Actually, this is only first part has been covered. So till now we have epilepsy. So epilepsy, if you go to hospital, then actually generally doctors see two important features. First is spikes in the data, EEG data, and second is large amplitude. So when we define features, we are equally motivated by these two features, they are clinical features. And when we're defining engineering features, we want to integrate that knowledge in the engineering feature. So these two features, till now, we have seen these two things, like epilepsy, and later actually this emotion, sleep states will come, then we will see other features of EEG. So it depends on the neurological condition. Epilepsy, these are the features. Different diseases have different features. Symptoms also.
Okay.
So one of the important actually direction is to come up with the engineering features which also integrate the this clinical features, clinical knowledge. That is important part.
Okay.
So then actually we are also including doctor's knowledge, and at the same time we are using engineering concepts.
So, for example, today internet addiction is becoming a major problem. So, can we, sir, successfully detect it using EEG signal?
Which is
Sir, internet addiction. So, because the person who are habitual to use it has a different EEG pattern, and the person, because it is major problem for the teenagers and students. So, can we, sir, uh, identify in the beginning, and so that the his parents or his guardian can be made aware that.
yeah, that is what actually. So this your intention of doing something that also can be predicted using EEG signals.
Okay, sir.
That is like if you are like addicted with something, that also actually that intention of doing something, some idea, thoughts are coming in your mind. That also can be actually detected with that. Even criminal minds, EEG signals are different.
So, sir, which type of alpha, beta, gamma, sir? How can we, sir? Is there any, sir, characteristics?
Yeah, that is actually so now depends on the nature disease so people they detect rhythms and then actually it depends whatever condition accordingly that actually the rhythms pattern changes. So it like criminal mind recently one of our work we have studied. So there we found different changes, different rhythms. So that actually, uh, it is clear that there is actually connection with whatever intention you have, whatever you want to do, stress, anxiety, depression, all these things they have well connection with EEG signals.
Sir, one more question. Is EMD analysis useful for speech pathology analysis from Krishna? Sir,
Yes, Dr. Hemant.
yes, sir.
Yes.
Sir, one another question from participant Krishna is, can we apply EMD analysis techniques for speech pathology analysis?
Yeah, that is actually a very important direction. So when you see speech analysis processing, lot of work is happening then. And speech now people want to do the vocal disorders that so when you have normal actually the signal processing signals and systems they are associated with each other. So when you are studying a speech signal, indirectly you want to understand the vocal tract. Similarly, when you are studying EEG signal, you want to understand the brain. Similarly, you are understanding ECG signal, you want to understand the heart. So if you have any vocal tract disorder or pathology speech, that will be reflected by the IMFs, intelligent mode functions. So that people actually they are applying this decomposition method and to detect the this vocal tract disorders or speech pathology, speech disorders based on this signal processing and machine learning techniques. Because your pitch will be different, formats will be different.
Sir, sir, another question from Ram Nivas. He is asking what patterns or features is more useful to identify the internet addiction using publicly available data set.
So these publicly available databases, they are well-behaved databases. They are actually nicely prepared by the neurologist. They have done manual analysis, so this is made up publicly available for the research. So and also if you have like you have developed any method which you study on the publicly available databases, that gives you an opportunity to assess assess the performance of your method with respect to other existing methods in the literature which have been studied in the same database. So that is publicly available databases good feature. But brain actually, like when you are studying for real life clinical applications, we should also do this study for our real life database. We should record at our place, our hospitals, and we should apply, validate with our real, our EG database. that we should record from our patients. Like for example, it has been whatever database I presented, and that has been done Germany, born in a hospital. So their patients are German patients, their brain signals, and we should also study them for our brains, our Indian brains, and then actually we should validate. But basic features of the diseases are same. So like you have epilepsy, then pattern is same, whether it is German or Indian, whatever, they have all neurons is synchronized together, generate very high electrical activity. So the way actually define the basic concepts are same, and but we should also validate with the public private databases also with the record in our hospitals. That is also important.
Sir, for example, when we want to develop our own database, when we have own our EEG machine, then sir, when we are recording the data set, sir, can we sir set the standards? Means, for example, uh, or we need doctor to validate it? Yes, that this thing is
Actually, the doctors, we need to validate that person has disease. So like hospital, doctor will tell you whether person has epilepsy or not. Once you have that information, then you can record signals for that person. So that is actually known that the person is epilepsy, having epilepsy.
so that is fine, sir. For epilepsy, it's a severe thing. But for example, sir, we want to create our own database among our student for internet addiction.
For
For identifying, sir, internet addiction.
addiction.
Yes,
Yeah.
sir.
Yes. So then actually, what generally doctors do, like for example, depression case, they have some form of questionnaire. They ask some questions based on that they detect. There are many manual methods, questions and answers they will ask. Based on that, they will tell you that whether person have addiction, person have, this intention, based on the questionnaires, and they detect. And some work actually we are doing with hospitals and doctors actually, and they want to know this from the EEG signal every time. So like the person is addicted with something, so they will record EEG signal, then they will give some, they will ask some medicines also, take medicines for some particular interval of time, and after that again come to hospital. Then again they will ask that questionnaire. So instead of that, they want to say they want to go for EEG recording every step to assess the monitoring,
Okay.
assess the addiction effect. So that actually this EEG signal processing is a very important part to monitor this addiction effect, addiction level of the addiction, level of the disease also, brain,
Okay.
any disorder. Sometimes doctors ask you for go for yoga, particular yoga. So how much yoga is done, and after doing yoga, what is happening? So after 15 days, they do some particular yoga and they go to hospital, and then they record EEG signal, and then. But the issue of EEG, what doctors are doing, they are questionnaires. They are asking questions. The form is there, then this patient will actually answer that questions. And based on them, they detect the person how much depression is there, how much addiction is there.
Okay, sir. So, sir, one another question, sir. Or, sir, if we can have break, 10 minutes break. I think it's too long for you, sir. We can join at 12:25 and remaining question we can take later.
Yeah, Professor Hemant?
Yes,
Yes.
sir.
Yes, please.
Sir, we have question. Sir, would you like to take question now, or we can take sir later also, because you
Later
can
also,
take
no
break.
problem. It is
Uh,
everything is no talk only.
no.
It's not
So,
a problem. Yeah. It's
so
actually
what?
main we
Uh,
should interaction is important part, no? That
yes,
is
sir. Absolutely. So, sir, what we can do, we can have some more question. Even I will ask other participants to write down the question, and then we can have questions in the last, and you can have the break for 10 minutes.
right now.
Sir, right now.
Yes. So after 10 minutes, then we'll meet.
So 12:25 we will join, and so
Okay.
other can also think, so we can take the questions in the last.
Okay. Okay. Okay.
Okay.
Thank you. Thank you.